So hi students, in the last class we discussed about the what is meant by logic family and what are the different types of the logic families available. At the same time, so what are the basic differences, what are the different logic families as available simply. So they can be categorized by using elements, that is maybe using BZT or FET. So the BZT can be again divided into two types, that is saturated logic family and non-saturated logic family. So in the saturated logic family, we have to discuss about that in the previous session. So that is what is meant by RTL family and what is meant by DTL and what is meant by DCTL and what is meant by DCTL. Up to DCTL we have to discuss in the last session. So in this session we discuss about what is meant by TTL logic family. So TTL logic family, very important thing, that is transistor logic. So among all logic families, the TTL logic family is most familiarly used logic family. So compared to all saturated logic families, nothing but among these all, so this TTL logic family is very convenient to use. At the same time, the speed of operation will be more. So compare with the remaining logic families. So simply we have to say that in our, so the mostly used logic family is simply a TTL logic family. So TTL logic family simply, so we can say that the TTL logic family nothing but, so that is the transistor logic. Here the only transistors are used for designing of this logic family. So nothing but the transistors are plays a major role. So these logic families are mostly used for NAND gate and NOT gate design. So by using this logic family, we have to design NAND and NOT gate. So that is about this TTL logic family. Let us discuss about that TTL logic family. So simply, so the TTL logic family is high power consumption. So compared to this, so the TTL logic family having several subfamilies. So it is also having several subfamilies. The subfamilies are standard TTL and Schottky TTL and low power TTL, at the same time standard low power TTL. So many types are available in our day-to-day life. Nothing but the TTLs are again divided into so many types. So advanced TTL, at the same time Schottky advanced TTL. So there are so many types available in the TTL logic. So let us discuss about the one of the logic family, that is one of the logic type totem pole NAND gate. That is by using this totem pole NAND gate. So this TTL family is known as standard TTL logic. So this particular gate is known, this particular family is known as standard logic. So this can be used for designing of the NAND gate. So this particular logic family is used for the designing of this NAND gate. So why this is known as totem pole? Why this term? So totem pole. What is meant by totem pole? Simply we have to say that. So here I am using this two emitter transistor. So that means this transistor consisting of two emitter terminals. The output of this one is given to the transistor Q2 and the Q2 collector terminal is connected to the Q3, as like that the Q2 emitter terminal is connected to the Q4. Here the Q3 and the Q4 both are, so one of the transistor is in on condition, obviously another one goes to the off condition. So that's why this connection is known as totem pole connection. Simply this totem pole connection is divided with this diode. Nothing but this diode is used for this splitting of Q3 and Q4. So obviously one of the transistor is in on condition, another one goes to off condition. So that's why this particular condition is known as totem pole connection. So let us discuss about this operation of this particular totem pole connection. Simply we have to say that in the totem pole connection, the first thing, that is this Q1. So this Q1, in this Q1 is consisting of two diodes, that is diode D1 and D2. These two diodes are used for this removing of spikes. So these particular diodes are used for this removing of spikes. So after that, simply this circuit can be acts as AND gate. So that is like a diode AND gate. It can be works like the diode AND gate, like this. So in the diode AND gate, what is an operation of the diode AND gate? Same thing will be follow here also. So this connection, that is the Q1 connection, is acts as DTL logic, that is diode logic, like this. Simply this can be like this. So here we apply input at this cathode terminal. So at the same time the anode terminal will be connected to the ground. So it can be performed like an AND gate operation. So the final output will be a NAND output. How it produce the output of the NAND signal? Let us discuss. So in the first condition, my VA and VB inputs will be 0, 0. So that is the VA input will be 0 and VB input will be 0. Obviously the Q1 condition will be, what happens? Simply, so we apply a VCC voltage at the base end, that is the base, and the emitter will be 0. So this is 0, 0 voltage is applied to here. Obviously the transistor is going to, what happens? There is a condition here, simply the transistor going to off condition or on condition. Simply it can be on. So when the transistor is in on condition, it can be replaced with the short switch. When it goes to a short switch, here the output of this collector Q1 is given to the input of Q2. So in this time the Q1 is in on condition and Q2 will be off condition. Why? Because the output here we have to take at the output of Q1. So when transistor Q1 is in on condition, obviously transistor Q2, that is the voltage is very less. This is applied to the transistor Q2. Then Q2 goes to off condition. When the Q2 goes to off condition, what happens? When the Q2 goes to off condition, simply here the voltage will be VCC. Why? Because the off condition nothing but it can be replaced with the open switch. The Q2 can be replaced with the open switch. So this can be given to the transistor Q3. So then Q3 is on condition. So when Q3 is in on condition, simply it can be replaced with a short switch. So that is in that particular time Q3 is on condition. In that particular time the diode D. So this diode is used for splitting of this totem pole connection. So here the diode D can be used for this. Simply this VCC voltage is given to the anode of diode D. So diode D is also in on condition. So this VCC voltage is produced at this output side. So in that particular time, what is the condition of Q4? So simply the Q4 is in off condition. Why? Because Q4 is in off condition. So when transistor is in off condition, that is here the transistor Q2 is in off condition. Obviously we can say that here the voltage will be VCC. So it can be replaced with the open switch. So that's why this VCC voltage is not reached at this emitter side. So that's why we have to say this transistor Q4 is in off condition and the final output voltage will be VCC. So that is when the input will be 0, 0, the output of the NAND gate will be 1. So that is the condition of this first condition. Next we give the 0, 1 input. So when we give the 0, 1 input at the time also, so that is 0, 1, in that particular time also, here the voltage will be 1 and 0. So obviously transistor is going to on condition. That is Q1 transistor is in on condition. When the transistor Q1 is in on condition, this collector voltage will be, this particular collector voltage will be VCE saturation. Why? Because it can be replaced with the short switch. This VCE voltage is given to the transistor Q2. So then what happens? The Q2 becomes off condition. Again same process, that is Q2 becomes off condition. When Q2 is in off condition, then Q3 on, and Q4 is in off condition, then the output voltage is VCC, that is 1. And the next condition, that is VA and VB will be 0, same process will be continued. And the last one, that is when both the inputs will be 1, 1. So when both the inputs will be 1, 1. So we can say that so anode voltage, nothing but the base voltage and emitter voltage both are same. So as per the principle, the base voltage is greater than that emitter voltage, but it does not satisfy that. Simply we have to say that in that particular time the Q1 is going to off condition. When Q1 is in off condition, so its collector voltage, what is this collector voltage? It can be generally open circuit. This collector voltage will be VCC. So this VCC voltage is applied to the transistor Q2, then Q2 is going to on condition. When Q2 is in on condition, what happens? When Q2 is in on condition, this can be replaced with a short switch. So this can be replaced with a short switch. This VCC voltage is flowing to here, that is given to the transistor Q4. And in that particular time, the Q3 will be off condition and Q4 will be on condition. And what is the diode condition? In that particular time, the diode is also off condition. So that's why simply they can be replaced with a open switch. Here in that particular time, the Q3 is and diode is replaced with a open switch. So simply the output voltage we have to represent will be 0. Why? Because it can be replaced with a open switch. So simply the output will be 0. So that is it can be replaced with the logic 0. So this is the totem pole NAND gate connection simply. So the operation of the totem pole NAND gate. But here it is having some advantages. What are the advantages of the totem pole? That is power dissipation. So coming to the totem pole connection, the power dissipation is very less. So at the same time, so it can be, so coming to the disadvantages, the totem pole connection here. So during the transition of low to high, so nothing but during the transition of low to high, somewhat Q4 is slow compared with the Q3. So maybe Q3 and Q4 will be on at the same time. So when during the transition, so Q4 is somewhat slower than compared with the Q3. So in that particular time, Q3 and Q4 is on at particular situations. So due to this condition, we can say that the power consumption will be nothing but it produces more power. So this is a major drawback of this particular condition. And the totem pole outputs are not wired. So wired ANDed, nothing but here the major problem of this particular one is wired ANDed. So that is a major problem of this particular totem pole connection. And but it is having most advantage thing, that is it produces a fast operation. So the operation of this totem pole connection is very faster. So that is an advantage of this totem pole connection. And next we discuss about that next connection, that is open collector. So this open collector, this can be avoid drawback of the wired ANDed. So here simply we have to say that the problem of this wired ANDed can be overcome by using open collector. But here the problem will be compared to the previous one, this operation will be slow. So compared to the totem pole connection, this operation will be slower. Simply this open collector logic is used for the NOT operation. So this open collector logic is used for this NOT operation. So for what is the purpose of this? Simply we have to say that, so why it is called as an open collector? Simply at the first condition, so it can be also known as open collector inverter circuit. So simply we have to say that inverter nothing but NOT gate. So in that particular condition, the output, so this output is we have to take at the output of Q4. So this Q4 is connected. So this can't be connected to any VCC or simply it can be available without any connection. So that's why it is known as open collector. But at particular time when without VCC we don't produce a correct output for this condition. So that's why I'm adding a pull-up resistor. So through with VCC. So here the pull-up resistor is used for the particular operation. So for correct operation we have to add a pull-up resistor here. So this pull-up resistor is used for the operation of this Q4. So without open circuit, and so this can be acts as like that. That is, it can produce a NOT gate. Simply we have to say that when we give the input, that is 0. So that is 0. Here the 5 volts is applied and 5 and 0. So that is simply we have to say that 5 and 0 nothing but the transistor is going to on condition. when transistor is going to on condition, this voltage will be VCE sat. This VCE sat voltage is given to the transistor Q2, then Q2 is in off condition. When Q2 is in off condition, what happens? When Q2 is in off condition, here, so another terminal, that is the Q4 is also in off condition. Why? Because when Q2 is in off condition, the emitter terminal of this Q2 is connected to the Q4. That's why the Q4 is also off condition. So then the output will be simply, we have to say that these VCC voltage we have to produce at this output. So that is whenever the input signal will be 0. So when we give this input signal as 0, then in that particular time the Q1 is in on condition. When Q1 is in on condition, simply the output voltage will be VCE sat. This VCE sat voltage is given to the transistor Q2. So then Q2 becomes off condition. When Q2 is in off condition, Q2 emitter terminal is connected to the Q4. So that's why the Q4 is also obviously off condition. When any transistor is going to off condition, so maximum the collector voltage will be a VCC. So that is when we give the 0 input and it produce the output 1. So at the second condition we give the input 1. So during that time the base voltage is 5 volts and the collector voltage is also 5 volts. So in that particular time both the transistor, nothing but transistor is going to off condition. So when transistor is in off condition, simply the output voltage will be VCC. So this VCC voltage is given to the transistor Q2. So then Q2 is going to on condition. So when Q2 is in on condition, here the emitter voltage, nothing but it can be replaced with the short switch. So this VCC voltage is given to the Q4. So during that time the Q4 is also on condition. So that's why when any transistor is in on condition, the output is simply VCE sat. Simply the VCE sat nothing but 0.3 volts. So the 0.3 volts, as already we have to discuss that, the 0.3 volts simply we have to represent with so that is with logic 0. So that's why this circuit can be acts as a inverter. So that is here the major drawback of this open collector is, so it can be eliminated, nothing but wire unding problem will be eliminated by using open collector logic. So but here the speed of operation will be very less. So that is a major drawback of this open collector logic. And mostly TTL gates are used for the NAND and NOT gate designing only. And next the final one is the transistor logic, that is tri-state. So what is meant by tri-state? So actually we have to know about the two states, that is either logic 0 or logic 1. But what is the third state? So that third state is known as high impedance state. So is it clear? Simply the tri-state means a state of logic other than 1 or 0. So maybe the output will be either 1 or 0 in which there is a high impedance state. So this state is known as high impedance state and there is no source and the sink at the output stage of transistor. Simply we have to say that this can be, so either, so not a 1 or an output will be not a 0. So this particular state is known as a high impedance state. So here we use that state tri-state. So in the tri-state, the major advantage of this tri-state one is simply in the tri-state, so it is an advantage of both totem pole as well as open collector. Simply the totem pole we have the problem, that is speed of operation will be more. In the open collector it eliminates the wire unding problem. So that is here the tri-state consisting of these both advantages. Simply we have to say that in the tri-state the output is simply, so the output will be faster operation, it can perform very faster and wire unding problem also eliminate here. So that is the advantage of this particular thing. At the same time here the tri-state connection will be, so simply we have to say that based upon this enable signal, so we have to control this operation. So whenever the enable signal will be 1, so during that time, so this particular tri-state connection can be replaced with that is this particular operation is like a NOT gate operation, and whenever the enable signal will be 0, so in that particular time it can perform the high impedance operation. So that is about the operation of the tri-state connection. And there is another one, that is Schottky TTL. So that is one of the unsaturated logic family. That is so that is a non-saturated logic family. Compared to the saturated logic family, non-saturated logic families are very faster. Why? Because so compared to the non-saturation region, the time taken to go to a non-saturation region is very simple. So in the next class we discuss about the Schottky TTL. So in today's class we discuss about the Ecl logic. So Ecl nothing but emitter coupled logic. So what is meant by Ecl and how it can be designed? Simply we have to check the operation. So Ecl nothing but emitter coupled logic. So here, so among these all logic families, Ecl logic family are very faster. So at the same time it can be operate with a negative logic. So the major thing about this Ecl logic family is it is operated with a negative logic. So as like that we have to discuss about the positive logic. Like that the Ecl logic is operate with a negative logic. At the same time here the currents kept high. So we have to place the currents very kept high. At the same time the major advantage of this particular one is simply so transistor is never going to saturation. That's why speed of operation will be more. At the same time logic levels are negative. So this is very peculiar behavior like that, that is which is operated with the negative logic. But it is also having some drawbacks, that is cost is high. At the same time noise margin, the noise margin of this particular Ecl logic family is very high. At the same time, so the high power dissipation and it's a negative supply. So due to this negative supply, it is very difficult to design. So that is about the major things about the Ecl logic family. And the Ecl nothing but emitter coupled logic. So it is a negative logic, but it is having some particular things, that is so simply we have to say that is operation speed is very high. Why? Because we don't go to the saturation region, that we have to use a non-saturation. Like we have to say that so here the transistors will be operated in the active region only. So that is a major advantage of this particular Ecl logic family. Let us discuss about the operation of this Ecl logic family. So here, so the Ecl logic family or Ecl logic gates is used for designing of, so which gate? Simply by using Ecl logic family we have to design both NOR and OR gate. So here this logic family is used for designing of NOR and OR gate. So let us discuss or let us draw the diagram of this particular one. Simply here it consisting of the input side, it consisting of the three transistors. So these three transistors forms a differential amplifier. What is a differential amplifier? So simply we have to say that it produces the difference and it compares the inputs. Among these, which one is high, it produces that particular output. So it consisting of the three transistors. These three transistors forms a differential amplifier. So that is Q1B, and this one is, I take it as A and B. At the same time, this is transistor 1 and this is also a transistor 1. And here I am connecting another transistor, that is transistor 2. That is we have to represent with the Q2. So this Q2 voltage is always minus 1.3 volts. We have to indicate that one, that is minus 1.3 volts. So we have to always indicate that thing. And here I am connecting emitter resistance RE. So this RE value is 1 kilo ohm, and the current flowing through this will be IE is equal to 3 milliamperes. And this one will be connected with each other. After that, here I am connecting a resistor with 300 ohms. That is R1 here, R2 is also a 300 ohms. Here I am using a negative supply, nothing but which is connected to the ground, and this one will be connected to with a minus 5.2, that is a supply, and output of this one, that is output of this particular transistor, these two will be connected with each other, and this one will. So the output of this one is given to the first transistor, that is Q3 base terminal. Here this one is the output. This output is NOR output, and this will be a 1.5 kilo ohm, as like that. This will be a Q3, and this one will be the output of this, will be connected to this, and this one will be Q4, which is output of OR gate, and finally this is the circuit diagram for this particular one. And here this is operated with a negative logic, that is minus 5.2 volts, and this is the circuit diagram of the Ecl logic. So let us discuss about the Ecl logic. Simply we have to say that in the Ecl logic, so in the Ecl logic, the first three transistors, that is Q1A, Q1B and Q2, acts as a differential amplifier. So here it can be like that, that is it can be differentiate the input voltages, based upon that it produces the output. At the same time the transistor, so Q3 and Q4 forms a emitter follower circuit. Here the output is taken at the emitter terminals of the transistor Q3 and transistor Q4. So let us discuss about the operation of this here. Simply, which is operated with a negative logic. In that logic, we have to indicate that logic 0 is represented with the minus 0.8 volts or minus 0.9 volts, and logic 1 will be represented with the minus 1.7 volts. So that is the major thing here. Simply we have to say that here the logic 0 is represented with minus 1.7 and logic 1 is represented with the minus 0.9 volts. So here when we get that output, simply we have to say that it is logic 1 and logic 0. So first I am giving an input signal of A and B. So that is A, B will be 0, 0. So 0, 0 nothing but, here the 0 nothing but minus 1.7 volts. So this 1.7 volts is applied to the both transistor, that is Q1A, Q1B emitter base terminals, and obviously the Q2 will be minus 1.3 volts. So we don't change that condition, that is the standard one. So in that particular time, it differentiates the input signal, nothing but it compares the input signal. During that particular time, what happens? The Q2 will be conducting. Why? Because compare this Q1A and Q1B, the Q2 signal will be more. So that is the input voltage will be more. So that's why the VA, that is Q1A will be off condition and Q1B will be off condition. So as we know that when transistor is going to on condition, simply we have to say that the IE current will be IC. At the same time, this current is known as I1 current and this one is known as I2 current. That is IC1 and IC2. We have to say that. And I1 is combination of I1A and I1B. Why? Because so this is combination of this collector and this collector current. That's why I1 is a combination of I1A and I1B. Simply we have to say that during that particular time when we give the input signal, that is both will be 0, 0. In that particular time this transistor is going to off condition. This one is also going to off condition. But transistor Q2 is going to on condition. Whenever the transistor Q2 is in on condition, what happens? When this transistor is going to on condition, this 3 milliampere signal will be reached at the IC side. Why? Because when transistor is in on condition, that is IC is equal to IE. So in that particular time, here the current will be generally 0 milliamperes. Why? Because so this 0 milliamperes nothing but both the transistors is off condition. That's why the collector current will be 0. When that I1 current will be 0, here there is any drop at the resistor, simply that is 0 into 300 ohms. There is no drop at this resistor. So here we have to connect a that is terminals minus 5.2 and ground. Simply we have to say that will be a 5.2 volts. So this 5.2 volt signal will be reached here. So nothing but there is no drop. That's why these 5.2 signals will be reached here. This is given to the transistor Q3. So obviously we know that the transistor Q3 is going to non-saturated region. Nothing but transistor Q3 going to active region. So when any transistor is going to active region or saturation region, the base emitter junction must be more than 0.7 volts. Here we have to say that this voltage that is more than 0.7, we assume like that is minus 0.8 volts. So the remaining voltage that is 5.2 minus 0.8. So whatever the remaining voltage present, that will be produced here. This will be remaining voltage drop is produced at the 1.5 kilo ohms. But here we have to take the output voltage. What is the output voltage? Simply we have to say that the output is taken at the emitter terminal of the transistor Q3. So here the emitter terminal of the transistor Q3 is connected to the negative one. Here the negative terminal is that is minus 0.8 volts. At the same time this voltage is given from here. So if there is any voltage drop here, that can be also present at the output side. So in that particular case there is any voltage drop here? No. So why? Because the current will be 0. That's why there is no voltage drop here. So that's why the output minus 0.8 volts and the drop will be under particular condition, that is minus 0 volts. Simply we have to say that is minus 0.8 volts. So that is the NOR output function. Simply the input will be 0, 0. The output will be minus 0.8 volts. Simply we have to say that is logic 1. So during that time also we have to know the condition of Q4. What is the Q4? It can perform the OR operation. So what is the OR operation? We have to check. So first we have to check the Q1A and Q1B condition. Then we move on to the Q2 condition. So that is minus 1.3 volt signal is given to the transistor Q2. So it compares the Q1A and Q1B signal. Then Q2 is going to on condition. When Q2 is going to on condition, this 3 milliampere signal will be reached here. That is 3 milliampere signal will be reached here. So that's why the drop across the R2. What is the drop across R2? R2 drop will be that is I2 into R2. What is the I2 value? That is 3 milliamperes and R2 will be 300 ohms. That is minus that is 0.9 volts. So that 0.9 volts drop is present in this particular, that is 0.9 volts and plus and minus. So whatever the remaining voltage, here generally the voltage will be 5.2 volts. What is the remaining voltage? 5.2 minus 9. So that is simply it can be a 4.3 volts. This 4.3 volts is given to the transistor Q4. So then Q4 is also going to active region. Why? Because so more than 0.7 volts, whatever the input voltage we have to give that particular transistor, obviously the transistor is going to the non-saturation region, nothing but it going to the active region. So when the transistor is going to the active region, so there is drop at this particular condition. This drop is generally so more than 0.7, that is we have to take it as 0.8 volts, that is a plus and minus. Finally the output here is we have to take that one, that is minus 0.8 volts, and if there is any drop at the resistor R2, that can be also present here. So there is a drop at the resistor R2, the drop will be minus 0.9 volts. Simply that is minus 0.8 volts and minus 0.9 volts. Simply the output is minus 1.7 volts. That is when both the inputs will be 0, 0, the NOR operation, so the NOR gate is produced minus 0.8 volts. That is minus 0.8 volts nothing but logic 1 and minus 1.7 volts nothing but logic 0. So that is the condition of this particular, so first condition. Let us check the next condition, that is when both the inputs will be 1, 1. So that is Q1A will be 1 and Q2 that is A will be 1 and B will be 1. If you know the operation of that first one condition clearly, then you have to solve the remaining one. That is 1, 1. In that particular time, we have to give minus 0.8 volts here. Here also we have to give the minus 0.8 volts. So again it compares the input signals. So that is it performs the differential operation. So simply it compares the input signal. That is minus 0.8 volts and minus 0.8, and QT will be minus 1.3 volts. So these comparison will be done here. So that is the transistor Q1A is also on condition and Q1B also going to on condition, and Q2 is going to off condition. Why? Because so compared to these voltages, the Q2 voltage will be very less. So and this 3 milliamperes is going from this Q1A and Q1B. Simply here the voltage drop will be 3 milliamperes and 300 ohms. That is 0.9 volts. So this is given to this whatever the remaining voltage. Here the remaining voltage in that particular condition will be so 5.2 minus 0.9, that is 4.3 volts. So this 4.3 volts is given to the transistor Q3. So then Q3 is going to active region. This whatever the input voltage, that is minus 0.8 volts, and the drop at this I1 will be minus 0.9 volts. So this is present at the output side simply. So that is minus 0.8 volts and minus 0.9 volts. That is minus 1.7 volts. So that is when both the inputs will be 1, 1, the output will be minus 1.7. So that simply it produces the logic 0. In that particular time, the transistor Q2 is off condition. That's why there is no voltage drop here. So simply the output will be minus 0.82 volts. So in the particular time, the output will be logic 0. Sorry, logic 1. Why? Because we get that output. So minus. So that is the output will be minus 0.8. So the output will be a logic 1 0. So this is about the operation of the Ecl logic. So in the next class we have to discuss about the operation of the Schottky TTL as well as CMOS logic. So thank you.